Afternoon. So welcome back, everyone. Today, before we start on the new subtopic, I would like to discuss on the previous exercise. Okay, on this January 2019, you were asked to do on question A and B. Okay, and I provide to you the solution. Okay, from the solution, there is a typo on the solution. Okay, let me see. The ratio given. Yeah. Okay, this part, the molecular weight of the fuel. Okay, the typo on molecular weight of the fuel, and then this one, mixture. Wait, see. Okay, sorry, which question again, Chinwe? This one, 2018. Not 19, right? See. 18. Okay, the typo is from 2018, where the question given is 0.78. Okay, 0.78, but from the solution, it is 0.82. Okay, so this one should be 1 minus 0.78. Okay, and then second part is the molecular weight of the fuel for part B. Okay. Okay, I'll share the correct answer from Yunhei. Thank you for your updating me. Okay. (2018). Okay, the error on 2018. So this is the correct answer for 7078 propanol. So for the rest, 1 minus 0.78. So you will get 0.22 of butane. Because the mixture it mentioned 0.78 propanol. Okay, so to get the new molecular formula for the fuel, okay, for the mixture, you need to get the new molecular formula for the mixture. Then from there, calculate the A. From the A, you can get the air-fuel ratio. Okay, so basically these are the answers, the correct answers. For 2019. Any question for this one? 2018. Okay, correct on the typo for the ratio. Yes. The what? I uploaded this one in Teams. This one. I already removed everyone. This one uploaded after the class that day. I will upload this in CN as well. Okay. Okay, this one has been uploaded in Teams last time. There's a typo for this part. So the correct answer is from this. Okay, I will upload everything. Okay. Now this one is 2018. For 2019, you are given mixtures of fuel as well. Okay, and you are asked to do A and B. Given answer for 2018 and 19. Okay, this one for 2019, no issue. So you should derive the mixture molecular formula. Okay, for this part. Derive the new molecular formula, then solve for the stoichiometric combustion, where you get the A. You need to find the A, okay, and generate the stoichiometric combustion equation with the mixture. For B, you are asked to find the AF stoichiometric using the A calculated, the A value calculated in the above part. Okay, plug in into the formula over here. Then you will get your AF stoichiometric. Okay. Any question for this exercise now? Last class, it was until A and B only, because C we haven't touched yet. Today's topic, we will focus on the C part, on the combustion product. Okay. Now for C, we go to this new slide. In this topic, we will focus more on the products. Once you have generate your stoichiometric combustion equation, so you will know how many moles of your product gases produced. Okay, so from there you can calculate and identify the mole fraction of your gases, be it in wet basis or dry basis. Okay, consider a simple combustion system using CH4 as fuel. From here, you generate the combustion equation, the stoichiometric combustion equation. Okay, we have done this in previous chapter. How this it can get to? Where these two come from? Where these two come from? This is the generated stoichiometric combustion equation. Okay, where these two come from? A, yes, correct. A, this is the A, where you should calculate it based on this equation. X from the fuel. 1, Y, yeah, 4 over 4. So that's how you get 2. Okay? This one, 1 x equals to 1 over here. So that's why 1. So y over 2, you get 2. This part is 3.76a. Okay, that's how you get the 7.52. Now from here, you can see the mole of gases produced. 1 mole of CO2, 2 mole of H2O, 7.52 mole of N2. Okay, so the total mole of product, one total on the product, total up all together, you will get 10.52. This one is wet basis because you include the H2O. Okay, so if the question required dry basis, just remove the H2O from the calculation. This one. Exclude H2O, then you'll get the dry basis. Okay, any questions so far? Yeah. Now that is number of mole. When you are required to calculate the mole fraction, so we know that fraction, the required mole over the N total mole. Mole fraction of CO2 equivalent to number of mole CO2 produced over total mole. Okay, so you have 1 CO2 produced over total mole. So this is your mole fraction of CO2. This is wet basis. Because this total is from the wet basis. So if dry basis, your N total is different. Okay, notice the difference. Dry basis without the H2O in the total mole. So this is your mole fraction of CO2 in dry basis. Similar calculation for the rest of products. Mole fraction of H2O. Mole of H2O produced over total mole. Okay, this you'll get this. N2, mole fraction of N2. For dry basis, this figure. Yeah. Okay, easy, yeah, this part. Okay, now. Just now it is on start. Combustion at start. No excess air. Okay, now if the combustion process is excess by 20%, amount of air get excess 20%, where the theoretical air is equivalent to 120%. Okay, can understand how it gets 120? This is the A that we calculated. 1.2 is because it is in excess air. 1.2. If theoretical is only 1, theoretical is 1. Excess 1.2. Excess by 20%, 1.2. Okay, now, from here, you can get the actual A. By including the excess air. In the product gases, excess of oxygen is unknown. So we remain as B. This would be the rest here. This is the A. Then 3.76 here. Unknown is B. The amount of O2 in the product gases. Now still remember in previous chapter that we simply assume if 20% excess air, we simply assume on the O2, it will be 0.2. Right? Okay, that one is based on assumption. We assume 20% excess air, for the whole 20% excess air is being released. Okay, but in actual, we need to do the material balance. In actual, that's why here it puts B as unknown. So you will need to calculate the B. How to calculate the B? You can do O balance. Okay, to calculate the B, you do the O balance, atomic balance, where you have this side, left hand side, right hand side. Okay, 2.4 multiplied by 2 is oxygen. Now, plus this side, you have 2 oxygen from the CO2, 1 oxygen multiplied by 2. Okay, 2 from H2O, then 2B. 2B. So from here, you will get B equivalent to 0.4. Okay, then plug in into the main combustion equation the actual excess oxygen produced in the product stream. Okay, Ken, Ibrahim, is it clear? Any questions so far? Yeah. Now, once you have the mole of excess oxygen in the product gases, you will need to analyze on the dry basis and wet basis products. So for the dry, remove the H2O part. Okay, let's say this one for dry basis. So 1 CO2 plus 0.4 O2 plus 9.024 N2. You will get the total mole of this. Okay, so this is total mole, not yet the mole fraction. For the mole fraction, the mole of product over the total mole. Multiply by 100, then you will get this fraction. Okay, similar for O2, this one. How about N2? What is the mole fraction for N2? 9.024 over 10.424. Multiply by 100. What do you get? Okay. 86.57 in percent. Okay, in percent. So these are your analysis for CO2, O2, and N2. Okay, this one you directly calculate using the calculation method. Okay. Now for next slide, where you can also use to identify the O2 and CO2 in your flue gas using the chart. Okay, using the chart. Just now your combustion process is 20% excess air. This is 20%. This line, okay, this line, O2. This one line is O2 line for all fuel. These fuel lines is CO2 line depending on the type of the fuel. Okay, our fuel just now is natural gas, stage 4. Stage 4 under natural gas. So using 20% excess air, this is your O2 produced in flue gas stream, where this is around 3.8 to 3.9. Okay, exactly like you calculated earlier. O2, 3.8. Okay, almost similar to your calculation. This one only using the graph, the chart. Okay. Now going up to identify the CO2 produced. Here is the point. So here around, this is 9.6 parts. Your calculation is roughly around this figure. Okay. So you either can use the direct calculation or you can use this chart if you are given the chart. So it depends, the CO2, it depends to your fuel. Let's say your fuel is propane or butane. So you should refer to this line. Okay, to this line. Let's say your fuel is anthracite coal. So your CO2 falls in this line. Okay. Yes, because more excess air. More excess of air. So you have a lot of O2 in your product gases. Okay, any question? This figure, it shows you the x-axis is theoretical air. Just now, x-axis is excess air. Basically, they are similar, but this one is theoretical air. So if 20% excess air, theoretical is how many? 120. Okay, so theoretical is 120. Refer to 120. This line will be your O2. Okay, this line. Above here will be your CO2. So going straight up, roughly around what you have calculated earlier. This one is for O2. This is for CO2. Okay, for this chart, it also showed if your process is fuel rich. That means less of air. So less of air. So this side, you should refer to identify what is the percentage of CO produced. CO because it is incomplete, not enough oxygen. So CO will be produced and CO2 produced. Okay. Again, if you have fuel-rich combustion, that means you have less of air, not enough air to combust. So you will have CO in your product instead of O2. So that's why here, the line here refers to CO. From here, you can identify how many % of CO can be produced, will be produced if your combustion system is fuel rich, not enough air. Okay, so the percentage over here is based on dry. Based on dry basis. Okay. This based on dry. This one it doesn't mention dry or what. But from the figure, it is based on dry calculation. The figure that we found based on the dry basis. From here, the label, it doesn't mention whether dry or wet. Okay. Now there are few items that you will require to identify for the analysis of products combustion. Percentage of specific products such as CO2, O2, okay, and other particulate matters. CO if your combustion is not complete, if it is incomplete combustion. SO2 is depending on your fuel. Solid fuel, you will see the SO2. For natural gas, will you have SO2 in your product? Natural gas. Let's say you use pure natural gas. No, right? Because pure natural gas is what? Stage 4. Okay, of course, you don't see SO2 in your product. Okay, then you need to know what is the dew point of water vapor in the combustion products. And also the dry basis analysis. Okay. Now for this one, you are familiar with this equation already, right? The PV and RT, ideal gas law. Okay, for ideal gas, mole fraction, we know mole fraction in a mixture of gases at a specific pressure and temperature is equal to the volume fraction of the component. Using the PV and RT equation, okay, so for the mole fraction where mole of the specific component divided by total mole equivalent to volume fraction as well from this PV and RT. Okay, can get the relation? Because later on you will need to use this equation to find the dew point or the mole fraction. Okay, we know that fraction, all fraction is equivalent to 1. Now for the law of partial pressure, Total pressure is the summation of its partial pressure. So each partial pressure will have their own constant and their own mole. Okay, so partial pressure for the I component, assuming that it occupies the entire volume. So you will have the I component only. So for the partial pressure, to relate with the PV and RT as well, we will have mole fraction equivalent to the partial pressure. Okay. Now here we have Antoine equation to calculate the dew point of product gases. For Antoine equation, have you met this equation before? Where? Huh? Distillation, right? Okay, actually the Antoine equation, this number is not fixed. They have constant. This one A, B, and C. This number is not fixed. Actually, they have certain figures according to their component, its own component. This one, we only refer to H2O. Each component has their own constant value, the A, B, and C. Okay, so this equation is only fixed to the H2O only, water only. Okay, you cannot use this value for other component except H2O. Okay. The pressure is in bar, temperature is in K. Okay, using this example, we have propane as the fuel, burned with 61% of excess air. Combustion enters a combustion chamber at temperature 25 degrees C. Assume complete combustion and total pressure of this. So it asks you to determine the air-fuel ratio. Percentage of CO2 in the products and the dew point temperature of the products. Dew point. So this for C, you need to use the Antoine equation. Now for the air-fuel ratio, we know that the equation is this. Of 4.76 A molecular weight of air over molecular weight of fuel. Okay, so the unknown over here is A. Remember that you have excess of 61%. Excess air of 61%. Okay, first thing first, I will always advise for you to generate the combustion equation first. This one should always be the first step. Generate the combustion equation. From there, you can identify what is your A and what is the mole of product gases produced. Fuel is propane, C3H8. Excess air, so it will be 1.61. Z here is the A. Okay, don't get confused for whatever letter used here. This one is always the A. Okay, so this A, how to calculate this? This A, this part. Yes, this part is always for the A. X plus Y over 4 or 2? 4. Okay, so from here, x is 3 plus y is 8 over 4. Your A is 5. Okay, this is at start. A equals to 5. Now for the actual A, you need to multiply with the 1.61. So 5 multiplied by 1.61, you will get this. Okay, so this is the finalized combustion equation. You have your A, you have the mole of each product. Okay. Now from there, input your A into the AF ratio, multiply by molecular weight of air, which is 29, divide by molecular weight of the fuel. Okay, so this is your AF actual, because inclusive the excess air. Okay, take your time to digest first for the part A and how to get this combustion equation, everything. Okay, 5 minutes for you to digest before I proceed to the B and C. Okay, can proceed to B and C. Okay, for B, it asks you to find out the percentage of CO2. Percentage of CO2 in the products. So from the finalized combustion equation, we have 3 mole of CO2 produced. Okay, and total mole, here it mentioned, okay, here it doesn't mention whether in dry or wet basis. Okay, so if you give your answer in dry or wet, it's acceptable. From the solution over here, it includes the H2O. So this one in wet basis. Okay, so CO2 in wet basis would be 7.4%. Three over 40.32. Okay, up to that. Next is to find the dew point of the vapor pressure. So we know that from the PV and RT equation, mole fraction is equivalent to the partial pressure fraction as well. And H2O, total number of H2O in the product is known, which is 4 over N total, which is 40.32. Okay, this is known. Now we need to find the PH2O. This is the one that you are required to calculate. Partial pressure, you are required to calculate the dew point. Okay, to calculate the dew point, you will need to find the partial pressure of the water vapor. Okay, because this one you will refer in table, thermodynamic table. Now, partial pressure of H2O is unknown. You need to calculate, whereby the pressure, it is known from the given statement. 1 atm, 101.32 kilopascal. Okay. So from here, we find the PH2O, partial pressure of H2O. Okay, do the calculation, you will get this amount of PH2O. Okay, up to that. Now, once you get the partial pressure of H2O, we want to find the dew point. That means the temperature at that particular pressure. So we refer to table A.5, A5. Okay, here. A5 at pressure 10. So the temperature at pressure 10 is 45.81 degrees C. So this is your dew point. In your slide, it mentioned around 60 plus. Where is it? The pressure, the temperature over here, in your slide, 60 something. That one is wrong. This is the correct figure, 45.81 from table A5. Okay, correct that in your slide. This figure. This figure, it should be 45.81. using table A5 from the thermodynamic table. The table will be provided during your midterm, test, and final exam. Okay, any question so far? Similar to your thermodynamic, much more easier, of course. Okay, can we do this last example for today's class? Ethane. Okay, in this example, it used ethane as the fuel. C2H6. In midterm later on, if I don't give the chemical formula, would you be able to remember? Let's say ethane. What is the chemical formula? Propane, C3. How many hydrogen? 8. Huh? I give lah. Okay, I give, because this is not organic class. I give lah. Okay, so ethane used as fuel in this combustion. Volumetric analysis of the dry products yield this 10% of CO2, 1% CO, 3% O2, 86% N2. Okay, you have CO in your products and also O2. You have CO and O2. It asks you to calculate what is the percentage of excess air, air-fuel ratio, and the dew point. Okay, let's see the solution. From the statement just now, it mentioned dry. So there is no H2O measured over here. Okay. Okay, this one, first step, as always, you need to generate the combustion equation. Ethane is your fuel, okay, and this the air products. CO2, CO, O2, N2, and H2O. Generate the complete combustion reaction. Assuming here in this example, it assumes 100 K moles of dry product. So dry 100 K moles of dry product. So these all equivalent to 100 K mole dry product. Okay, now let's say equating coefficient for each component. For nitrogen, we have 86%, where we know this 86 is equivalent to 3.76 A. Correct. So this one equivalent to 86. So from here, you can get your A. Here we just use A. Okay. So your A, this is your thought A. Thought A or actual A? What do you think? Actual. This is actual A. Okay, this is actual A. Now for carbon, do the carbon balance. Left hand side, right hand side. Carbon balance. Okay, so this one on the combustion equation just now, it puts certain unknowns. A for the fuel, B for this one, okay, and this one of 10 is the one that generated from the statement. 1 CO produce 1%. So 3 is because of this. 86 over here. Okay. So now for the letter is confusing. Yeah. I don't want you to confuse. You just remain as B over here. Okay, this B equivalent to 20.87. Why it put A over here is because this one is basis for the products. We use basis on the products, not the fuel. Okay, basis on the products. So all of this is equivalent to 100 kmol, but we do not know how many mole of fuel. Okay, we are not sure how many mole of fuel being used to produce 100 kmol of product. So that's why here it put unknown. A, okay, unknown amount of fuel. Okay, then do the balance, left hand side and right hand side. C balance, you will get 2A. Okay, 2A from this left hand side equal to 10 multiplied by C plus 1 from the CO. Okay, so from here you get A is equivalent to 5.5 mole. Okay, the A. So in order to produce 100 kilomole dry product gases, you will need 5.5 mole of ethane. Can I up to that? A we got, B we got. Now the other unknown is C. C is the mole of H2O produced in the product gas. So to find the unknown of the C, how many mole of water over here, we do hydrogen balance. Left hand side, 6A, 6 multiplied by the A. Hydrogen, this side is 2C. Okay, 2C. 6A equals to 2C. A we already know, which is 5.5. So from here you can get the C. Now we have all the unknowns. A, 5.5. B is 22.87. C is 16.5. Okay. Input them into the combustion equation. A, B, and C. Okay. Again, I repeat, this 5.5 because the question mentioned product gases produced is 100 kilomole. Basis here used for the products, not on the fuel. In previous calculation, we use basis of the fuel. Okay, this one is basis of the product. That's why you have unknown mole of fuel over here. Now from there, this is the generated combustion equation. Next, simplify to 1 kmol of fuel. So all divide by 5.5. All divide by 5.5. So we simplify to 1 kmol of fuel. Once you have 1 kmol of fuel, then it will be easier to determine the excess air. So excess air over here, if theoretical, it is without the oxygen. Okay, this one is without oxygen. This one without oxygen. The start. This one with excess air. You have oxygen. This is the amount of excess oxygen, not the excess air percentage. Clear? Now, how to find the excess air? Remember the excess air equation? Okay, from here, it calculates the stoic. This is the stoic. Equation at stoic. So at stoic, just use the fuel CXH1 from the A. So you will get 3.5. This is at stoic. At stoic means at theoretical air. (3.5) is A at stoic, whereby you have calculated earlier A from excess air. So to calculate the excess air, the excess air, the A for excess air, this one A for excess air divided by A for theoretical. So you will get this 1.19. Okay, percentage of theoretical air, 1.19. Where we know that 1.19 is equivalent to 119 theoretical air. So 119 theoretical air is equivalent to 100 plus 19. Okay, 100 is the theoretical, 19 is the excess air. So the excess air percentage over here is 19%. Okay. Okay, take your time to digest first. This part is a bit confusing. Okay, clear this part? To determine the excess N. For the FU ratio, similar equation. Okay, where you need to find the A. Okay, we have the A. Where is the A? Here. This is the A that we get from the finalized combustion equation. Okay, this is the A, 4.16. So incorporate into this equation 4.16 multiplied by 4.76 molecular weight of the air over molecular weight of the fuel. Then you will get this AF ratio, FU ratio. Okay, for the dew point, using this equation, NH2, we know it is 3, and total from the summation of the mole produced. Okay, this one is based on wet basis. Okay, wet basis. Total pressure given at 1 atm. So from there you can calculate the partial pressure of the H2O. Then once you get this budget pressure for H2O, 14 kPa, refer to table A5. Okay, you will get this figure, 52.34 from A5. Okay. Okay, so I'll stop here. Do you have any question before we stop the session? Okay, no question. So we will continue our class with the next example over here. Okay, that's all. Thank you.